going to talk about little bangs in the laboratory and how they tell us about the evolution of the universe subsequent to its creation. But before I begin, I would like to share something from Dan Brown. And we must appreciate the content of what is written here. All questions were once spiritual. Since the beginning of time, spirituality and religion have been called on to fill in the gaps that science did not understand. The rising and setting of the sun was once attributed to Helios and a flaming chariot. Science has now provided answers to almost every question man can ask. There are only a few questions left, and they are the most esoteric ones. Where do we come from? What are we doing here? What is the meaning of life and the universe? And as we proceed to answer those questions, all what the answers do is raise more questions. So we want to determine what happened after the evolution of the universe and see what can be learned in the laboratory regarding the evolution of the universe. And we will use the scientific method in our pursuit. So what is the scientific method? It is based on observation and measurement, on building a hypothesis that should be falsifiable, which means it should be able to make predictions which I can test and see whether the hypothesis is correct. And at the end of it, the hypothesis should also have an attribute called the universality attribute. This is slightly less commonly known, and what the universality attribute means is the following. Most of us have seen a rainbow like this. Depending upon our literary talents, if I ask you to react on this rainbow, everybody is going to write a different couplet, different poems, whatever. If you ask different children to react on this, they will all have different behavior. But if you ask physicists, please describe the formation of the rainbow, every physicist on the globe will give you the same description. Now, that is science. It has a universality. There is an objectivity. And we should remember this every time we discuss what is science and what is not. So the question is the scientific method applicable only to science? Well, the scientific method is a certain temperament, and that is not limited to science. To give an example from more daily life, you look for patterns or correlations in the winners of Miss World or Miss Universe. And you notice that in India, from 1994 to 2001, there were about 6 contestants who won the international beauty pageants. But prior to 1994, there was none. In fact, technically correct, there was one in 1968, Rita Faria, and after 2001, there have been none. Why? Is it too much of a chance that all the beauty contestants or everybody who won the beauty pageant were in 95 to 2001? Or is there more to it? So if you think about it, you realize that it was about 1991 that India opened its markets to the world. And what happened? Everybody wanted to sell their products in India. And obviously they wanted to sell the cosmetic products also. So if an Indian becomes a Miss World or Miss Universe, all of a sudden it sparks off million dreams and a new market has been created. A job well done. Now the point is, does this happen only in market forces, or do you see such patterns in everyday life? You see it everywhere. When you see it in nature, then you call it science. When you see it in social sciences, aspects like this, you call it social science. But it's the temperament that I wanted to underline. Now, using this kind of temperament, we now know nature over 40 orders of magnitude. Now, 40 orders of magnitude means we understand nature at the scale of 10 to the power of minus 18 meters, which is the size of the smallest particle or the constituent of matter that we know, up to 10 to the power of 26 meters, which is the size of the visible universe, one followed by 26 zeros. What is the difference between them? The difference is the larger one is what we call as cosmology, and the smaller one is what we call as high energy physics. I practice high energy physics. My religion is high energy physics. So what is the difference in these two? Other than the scale that they are different, when I start probing matter at these two different scales, then the tools are very, very different. One is a tool what we call as the Large Hadron Collider at CERN, about 150 meters under the ground, a 27-kilometer long machine. Okay, and that is the one which is used to break a particle into the most fundamental constituents, smaller than what you can conceivably imagine. And that is the reason you need enormous force to break those particles. The other is what is known as the Hubble telescope. So that we don't get any interference from the atmosphere, this is put 500 kilometers outside away from the surface of the Earth. And it is taking pictures from where? From the universe. From where? From nowhere. It's beyond stars. It's beyond galaxies. It is taking radiation from them and trying to determine what happened in the universe over last so many years. So experiments such as these two are the more current experiments, but experiments such as these and other experiments over the last few decades have told us something about the formation of the universe, and that is what we'll see. We understand today, and that is the current correct scientific wisdom, that the universe was created with a big bang. After the universe was created, space was created, time was created. Now this should shock you completely, because when I say space was created, what does that mean? When you say time was created, what does that mean? What happened before the Big Bang? Before is a word which doesn't exist, because before has something to do with time, and time was not there at the time of Big Bang. Okay, so even scientists escape there. They say, what happened at the Big Bang? Well, it's singularity. We do not know. Don't ask questions regarding that. We only answer questions beyond a certain time. Beyond a certain time is about 10 to the power of minus 30 seconds or so. So the universe expands. There is something called an inflation. The yellow part that you see here is essentially all radiation energy, light kind of a thing. Gradually, this energy is converted into matter. You have fundamental constituents like electrons, quarks, neutrinos. These are all the fundamental constituents of matter that we know. The system evolves, which means the universe evolves. It expands, and as it expands, it cools down. As it cools down, the temperature decreases and decreases to values so that these constituents can combine and form proton and neutron things that we, all of us, are made up of, and which are the things which actually give us the mass. So what is it that we want to do in the laboratory? Ideally speaking, in the spirit of science, when I do experiment, I say I will believe all this if I can reproduce all this, but I cannot recreate a universe. So is there something that I can do which would sort of replicate what is happening at the time of the creation of the universe and test this evolution that I see here? And the answer is, luckily, yes. And to be able to do that, we have to understand that we have been able to probe into the structure of matter to distances as small as 10 to the power of minus 15 meters and so on. So how have we been able to see at distances which are as small as 10 to the power of minus 15 meters? This thickness of a hair is of the order of 10 to the power of minus 6 meters. So we are a 1/billionth of a thickness of a hair, and we know what is happening there. So that is the achievement that we have. The underlying philosophy is luckily extremely simple. And to be able to see this underlying philosophy, we see what are these called as scattering experiments. There is this black piece of cloth behind which there is an object. And I want to determine what is the size of the object, what is the shape of the object. And I have no idea how to do it. So what I do is throw glass balls at it, tiny balls at it, and see how are they deflected. You see number one passes straight, number two is deflected at a certain angle, and so on. So I look at the way these balls are deflected at various angles to see what is the likely shape. And you can see that the likely shape is probably this kind of an ellipsoid. On the other hand, if they would have deflected differently, would the shape be any different? And that is what we see in the next figure. You see that the balls are deflected at different angles and the shape is something like a wedge. So given that this is the underlying principle that we adopt to know about the structure of the matter at the tiniest scale. So I know what is happening at 10 to the power of minus 15 meter by conducting experiments like this, with the only difference that the glass balls are moving at the speed of light and they probe really deep inside. technically correct, not speed of light, just less than the speed of light. So what do we know from all this? We know today that what you see in the left-hand side here is a proton. The green and the purple or the magenta things are what are known as the quarks and the antiquarks. And those spring-like things are what are known as the gluons. Depending upon viewpoint, somebody might say, what is this dirty looking thing? For me, this is a wealth of information. I could spend my life on this. And this contains so much of information. And these are the elementary particles which existed at the time of the evolution of the universe. So the question then is, can I do something with these particles to know the evolution of the universe better? And the answer is yes. All what I have to do is take in large number of protons and put all of them in the same volume so that the total energy becomes huge. Okay. Or the other option is take large number of protons in a nucleus, say for instance lead, which has about 200 of these neutrons and protons, hold it and squeeze it. But squeezing something which is 10 to the power of minus 14 meter is not so realistic. So what do? I take it and collide it with each other. Take two such nuclei, make them collide with each other, and then try to find out whether they are squeezed or they break up. Now, who decides what will happen, whether they'll be squeezed or they will break up? Something called the phase diagram. Now, what is this technical word, phase diagram? Luckily, this has an easy answer. In fact, physics is a very easy subject, so everything has an easy answer. So what you do is, you say, I have a glass ball and a tennis ball, and I drop both of them. Which one will break when they hit the ground will depend upon what is the phase diagram of glass and what is the phase diagram of the tennis ball. So that is the kind of thing that phase diagram tells us, and that is what we want to determine from the properties of the nucleus. How do we go about doing it? We do it in experiments like this. The Large Hadron Collider was the 27-kilometer long thing, which sent us nuclei moving nearly at the speed of light. They come and collide somewhere in the center of the red region. Thousands of particles are produced because all the energy has been converted, not all, large amount of energy has been converted into mass. So those particles fly around to various detectors. India has a very significant contribution in this. The two long blue arrows that you see were manufactured in India. The whole experiment as a whole took 20 years from conception to installation. And there were more than 1,000 people who worked on it for more than 20 years. So those are the kind of experiments that we are talking about. These are the experiments which really create completely new physics. How do these experiments work? How do these detectors work? Well, if I look at the figure on the left, I see contrails in the sky. It doesn't matter whether I see an aircraft or not, but the existence of contrails is an evidence in support of an aircraft. And there is a universality to this. Everybody agrees with this. Okay. Similarly, when particles move through certain matter, they make contrails, which is what we see on the right-hand side, except that we call them tracks. And then what happens is, depending upon the thickness of these tracks, how they are bent, etc., we determine what are these particles. So these are different particles called K particle, pi particle, kaons, pions, protons. And now what we do, we look at this figure for infinite number of hours to find out what is the pattern present there. And then we look at another figure. But notice this technology, illustrative as it is, unfortunately, if there are thousands of particles or tens of thousands of particles, this is not going to work. So we have electronic detectors, and electronic detectors record all the information and help me reconstruct an image like what I have on the right-hand side. Okay, with the help of advanced technology, I now have a three-dimensional image instead of a two-dimensional image, and that is what you see in the next. This is another picture which I love. This is an event called a nucleus-nucleus collision, where the two nuclei have collided, moving nearly with the speed of light. All the energy was initially in this direction. After the collision, the energy was converted into thermal energy, heating up, all sorts of things. Particles started moving in all sorts of direction, also in the perpendicular direction where there was initially no motion. The yellow lines are all different particles. The question for you, sir, is, do you see any pattern in this figure, or is it just random? And the answer is, not only there is a pattern in this, the pattern that I tell you that exists in this is the same pattern that every other physicist in the world will observe. Except that to be able to find out that pattern, it requires a lot of intuition, a lot of hard work, a lot of blah, blah. Okay? So what we do is we collect millions of these and look for patterns and provide a mathematical structure to that pattern so that everybody in the world agrees with this. And what do I get with those patterns? So here is a figure where, since all the energy has been converted into, not all, most of the energy has been converted into thermal energy, just like in the universe, thermal energy, there were radiations. Similarly, there are radiations here. I look at that radiations and find out what is the temperature of the source which was created in a nucleus-nucleus collision. And my pattern recognition algorithm, etc., everything tells me when I plot something called the transverse momentum or the motion in the perpendicular direction versus the yield, number of particles coming out, then I get that the source had a temperature of 304 MeV. 300 MeV is a temperature which corresponds to 10 to the power of 12 degree or more Kelvin. This is close to the second rung in that figure. So we have been able to reach levels which are beyond the two blue points, moving in the backward direction. And the next generation of experiments, we will further like to go back or closer to the origin of the universe. What is the purpose? The purpose is to understand the properties of the matter as they existed in that region. So is that all the result that we have? We have numerous number of such results, all different. I'm going to spare you the details of that. But each of these figures takes millions of events, similar kind of computing power, thousands of man hours, infinite number of discussions, fighting, everything. And finally, the result is consolidated when everybody in the world accepts that this is correct. So this is the kind of fun that we have. This is what I wanted to share. And just to give you a feel at the end of what we know about nature, I would like to share two quotes which I personally treasure. One was said by Francis Bacon more than 400 years ago. The subtlety of nature is greater, many times over, than the subtlety of the senses and understanding. In a sense, what Bacon is saying is, you cannot understand nature. 300 years later, Einstein says, the most incomprehensible thing about the universe is that it is comprehensible. It was only Einstein who could say, I understand the subtlety of nature. Thank you.